Hey guys, welcome back to chapter 17. In this video, I'm going to work another example using the Henderson-Hasselbach equation, and then just give you some facts about when we can use the Henderson-Hasselbach equation. Okay, so let's dive into a problem first. So why don't you guys go ahead and pause the video, get as far into this problem as you can, and then I'll catch up to you on the other side. All right, calculate the pH of a buffer solution that is 0.05 molar benzoic acid and 0.15 molar sodium benzoate. So first step is to write a chemical equation. Oops. Hang on, let me get out of here and get a blank screen to work on. There we go. Sorry about that, guys. All right, so the first step is to write a balanced equation. So we're going to start with benzoic acid. So the H, go back one, 752, so C7H5O2. So that is going to react with water. Find equilibrium. So this is an acid. So we're going to be left with the conjugate base of that. And water is going to act as a base, and it's going to accept a proton, so hydronium. Okay. And also, this is sodium benzoate. So for those of you that like putting that salt in there, when you write your equation, you can put that sodium in there if you like. It's completely up to you. Okay. So the first step is writing the balanced chemical equation. Next, we can dive right into our Henderson-Hasselbach equation. So pH equals pKa. So again, they give us the Ka value. So pKa is just the negative log of that value. So negative log of 6.5 times 10 to the negative fifth. So the pKa, 4.19, we'll say. So 4.19 plus the log of base over acid. Okay. So it tells us that it's 0.05 molar benzoic acid. So that's our indication, and that's the number that goes on the bottom. So acid's on the bottom. And 0.15 sodium benzoate. So now that we wrote our balanced chemical equation, we see that that is the conjugate base. So that's going to be the number that goes on top. So now it's just simply chug through it since we plugged our numbers in. So I'm going to do pH equals 4.19 plus log. I'm going to take 0.15 divided by 0.05. And this is 3. So pH equals 4.19 plus, I'm going to type in log of 3. And we get 0.4. Call it 8. So pH equals 4.19 plus 0.48, 4.67. Okay. So easy peasy with the Henderson-Hasselbach equation. Hopefully you guys are finding the beauty in that equation. Okay. So just some facts about this. So when do I use the full equilibrium analysis? So that 4-step problem versus the Henderson-Hasselbach. So Henderson-Hasselbach equation is generally good when the X's small approximation is applicable, when that works. Okay. So when does the X's small approximation work? So if the initial concentration of acid and salt are not very dilute, so that means that they're fairly concentrated. And then when Ka is fairly small. I will tell you that for my examples that I put out there, you can go ahead and assume that X's small approximation will work. I will do my very best to pick problems on Pearson and Chem 101 that also allow you to use the Henderson-Hasselbach equation. But if something wonky comes up on there and Henderson-Hasselbach is not working, just bring that to my attention so that I can get rid of those problems. But you can go ahead and assume from here on out that X is small will work, and therefore Henderson-Hasselbach will work. That's it for Henderson-Hasselbach. The next step in this chapter is looking at the pH of the original solution and then looking how that pH changes when we add a strong acid or how that pH changes when we add a strong base. I hope you guys found this helpful.